Sometimes when we do these electrophilic reactions, there are substituents already on the ring, and these have an effect sometimes on always where the electrophile adds, and sometimes it even affects whether or not the reaction can go ahead. So let's look at how we classify the substituents so that we can predict what's going to happen. There are two effects that we look at. One is activation or deactivation, and this really controls the speed at which the reaction can go. If the ring is activated, it means that the reaction will go faster than benzene ring. If it's deactivated, then the reaction would go slower or not at all in comparison to a benzene ring. Then the location of the ring where the reaction occurs is affected by the substituent, and it's affected either by being directed to the ortho para positions to the substituent already on the ring, or to the meta position from the substituent that's already on the ring. Activating substituents increase the reactivity by pushing electrons into the pi system, and the deactivating substituents make the ring less reactive by pulling electrons out. So the activating substituents are electron donating, and the deactivating substituents are electron withdrawing. What do we consider to identify how a substituent will behave? We look at the electronegativity of the atoms first of all. So fluorine, for instance, has high electronegativity, so it pulls electrons away from the ring. Whereas something like hydrogens are electron donating, and they push electrons into the ring. Hydrogens that are on a carbon is what we're talking about, and fluorines that are on a carbon. The non-bonding pairs on an atom that are adjacent to the ring can overlap with the pi system and interact by pushing electrons into the pi system, or donating electrons to the pi system. Pi bonds that are in conjugation with the ring can resonate. There is resonance that allows the electrons to that are in the pi system to be fed into the ring. The activating substituents are carbon chains, so that would be chains like alkyl chains, a methyl or butyl or T-butyl. Anything with carbon only and hydrogen on them are electron donators. A hydroxyl group is an electron donating substituent, and you may look at the hydroxyl group and say, but oxygen is very electronegative. That is true, and in some ways that reduces the activation that it could do, because the electronegativity of the oxygen is pulling electrons toward it. But there are non-bonding pairs on the oxygen that can be fed into the pi system, and that is more important than its electronegativity. So we find that hydroxyl and an alkoxyl both are electron donators. Nitrogen likewise can put its non-bonding pairs into a pi system. So if you have a nitrogen that has a non-bonding pair on it adjacent to the ring, it will be an activator. And it's even more of an activator than oxygen because it's less electronegative. If you have a double bond, so your carbon chain can either be an alkyl group or it can have a double bond in it. The double bond has a pi system in it that can push electrons into the ring, the pi system of the ring. So all of these are electron donating groups, and they all are activators. Deactivators are the electron withdrawing groups. Halogens are deactivators. Because they're electronegative, they are deactivators. pi systems that have an electronegative atom one away from the ring are deactivators, because what happens is that electronegative atoms is pulling electrons away through the pi system. A nitrogen with a positive charge on it. We were introduced last semester to tetraalkyl ammonium salts, and the nitrogen has a positive charge on it. Anytime you have 3 bonds to a nitrogen on a ring, there's a 4th bond there, and that puts a positive charge on it. That positive charge on the nitrogen essentially dampens the electrons from being seeking out the electrophiles. So it reduces the activation of the system. It is a deactivator. Halogens now are deactivators, but they're not super strong ones. They are more electronegative than hydrogen, and of course than carbon, but the non-bonding orbitals aren't really great at adding to the ring. So the electronegativity of the halogens pulls the electrons away through the pi system, and the non-bonding orbitals push them back in just a little bit. So what we find is that halogens are deactivators. Pi systems that have an electronegative atom one atom away from the ring are very serious electron withdrawing groups. So if this carbon were on a benzene ring, or a nitrogen like in nitro on a benzene ring, cyanide, a cyano group on a benzene ring, this would be an imine on a benzene ring. A sulfur with a double bond to the oxygen, as in the sulfonic acid. All these are going to be serious electron withdrawing groups, and they deactivate the ring a good bit. Of course, the positive charge is easy to understand why that would deactivate an electrophilic addition reaction. Okay, some groups will direct ortho and para. All of the activators you see here, oxygen adjacent to the ring, nitrogen adjacent to the ring, and carbons adjacent to the ring, all of these are activators, and all the activators direct substituents to be added to the ortho and or para position. Para is favored more because there's more room there. Ortho is adjacent to the substituent that's already there, so steric hindrance can play a part and reduce the amount that goes to the ortho position. But both usually are formed. So here's an example. If R is an alkyl group, it's going to be an electron donating ortho-para position director. So it's going to be faster than benzene because it's an electron donating group, and it will direct substituents to add to the 2, 6, and 4 position. So if you get mono addition, you're going to find sometimes it's here, and sometimes it's here. And again, I told you that the ortho position is usually in a smaller quantity than the para position because there's some steric hindrance between the electrophile being added and the substituent, the electron donating substituent. Okay, right here we're showing why the electron donation promotes ortho addition. The alkyl group, if you look at the electrophile being added ortho to the alkyl group, you can see that a positive charge would be on the number 3 carbon. Resonance would make that end up right here and right here. Well, here the positive charge is stabilized by the alkyl group, so this structure right here greatly enhances the stability of this whole adduct. However, if the substituent is added meta. So here the electrophile was added to the meta position. Where is the positive charge? Adjacent to where the electrophile is added. If I look at the resonance structures for each of these, you're going to see it puts positive charge here in the ortho position and positive charge right here in the position para to the alkyl group. That positive charge is going to be making those positions unlikely for electrophiles to be added to. But also, there is no positive charge being stabilized by this alkyl group. So it's not as stable as the previous slide when it was in the ortho position. In the para position, what you get is resonance that goes, so you have the electrophile add here. There's an unwritten hydrogen right here also, an unwritten hydrogen right here, and a positive charge in this atom. When this atom resonates, where does positive charge end up? Here and here. Right here, it's stabilized by the substituent that's in place when you start the reaction. Because this resonance structure has greater stability, it encourages this reaction to go faster, and it helps make this position and this position more likely for electrophiles to be added to those positions. So alkyl groups are orthopara, directing, and activating. You have a stabilized cation formed in the transition state when you have added your electrophile to the ortho-para position. So it is activated and it directs substitution to those places. The meta positions are not stabilized, and so they don't form very readily. And we see a similar thing happen for other substituents that are electron donating. So the hydroxyl group promotes addition in the ortho position, not in the meta position, but yes to the para position. So we find that when an oxygen is attached directly to the benzene ring, that we enhance electrophilic substitution in the ortho and para place. Okay, this summarizes that oxygen or nitrogen groups. This is where the oxygen or nitrogen is directly attached to the ring, are orthopara, directing, and activating. The reasons? They stabilize a cation at the ortho and para position, and even though they're more electronegative than a hydrogen, the non-bonding pair can be donated into the ring, and that actually activates and makes it more more sensitive to or more faster reacting with electrophiles. So just remember that those groups where oxygen and nitrogen are directly attached to the ring are orthopara activators. Halogens also direct to the ortho and para position. In the ortho position, you can see that the positive charge works its way around to the halogen, where the non-bonding pair can stabilize the positive charge there. But it is slightly electron withdrawing, and so it will not be an activator. In the meta position, the positive charge is never stabilized by the halogen, and in the para position, the non-bonding pairs, the positive charge can work its way around until it gets adjacent to the halogen, and then the non-bonding pair can stabilize that positive charge. But again, because they are more electronegative and the donation of that non-bonding pair is not really great, they have the atoms that are small are really electronegative, like fluorine, and the atoms that are bigger and not so electronegative have really big orbitals, and they poorly overlap with the pi system. So what we find is they're orthopara deactivators. So here are some examples of these reactions. Here we have a methyl group, which is an alkyl group, and it is an ortho-para director and an activator. So this reaction actually proceeds at a rate that's faster than plain benzene, and the products that you find are primarily ortho and para substitution to the methyl group. What you find is a slight excess of the para position because of the steric hindrance that you would have from the ortho location, but it's minor. One thing that we have found is that these right here are constitutional isomers, and as a result, they usually are very easy to separate. So we can separate them by chromatography or other methods, maybe like crystallization or something. Another example, here you see there's a carbon with a pi system because there is no electronegative atom here. This is an ortho-para activator, so the reaction is faster than plain benzene. These conditions put a nitro group on. Where does it go? To the ortho and para position. And again, the para position is slightly more slightly in excess of the ortho position. So you try this. What would be the outcome of this reaction? Okay, because bromine is an ortho-para deactivator, we would have the ortho and the para position substituted primarily. So we would get the ortho sulfonic acid and the para sulfonic acid. And this reaction would go at a rate that was slower than plain benzene.